This is part 2 of the vector math video. One thing I forgot to mention last time is that we can have positive vectors or negative vectors. For example, if we're still thinking of the tail-to-head method, what if we had vector A plus vector B? Okay, and let's say vector A was here, and vector B was this way, that long in that direction. Well, what we would do, just as a review, is to take either one of them first. Let me try vector B first, just for the heck of it. I'll just bring that over. There's vector B, keeping the same angle in the same direction, basically. I just slid it over to a convenient spot, and then I can draw the vector A. I can slide that over. I kind of put it in a bad spot here, but I'm going to continue with my mistake, and I'll just slide that over here so the tail of vector A touches the head of vector B, like that, keeping the same magnitude and direction. Now remember, my resultant of vector A plus vector B would just be, it looks like it's almost perpendicular, but it doesn't necessarily have to be. So it'd be something like that. So this would be my resultant. I'll just put R for resultant. But what if we have vector A minus B? Vector A minus B. Well, really, the vector math uses the same ideas that are used in algebra. You can have, positive or a negative variable, right? Okay, so this is the same thing as saying vector A plus a negative B. And a negative B is just the opposite direction. Okay? So what we can do then is just go ahead and let's say I want to draw vector A in first. I'll just slide. There's my vector A again. I don't know if I drew it quite the right length, but and then what I want to do is bring vector B down, but instead of touching the tail of it so it's going to the left, I'm going to do it so it's going to go to the right. Okay? So vector A minus B would be like this. Okay, this is a negative B. See, it's the pointing in the opposite direction. That's the negative vector B there. Here's a positive vector A, and now we can add the two vectors up by touching from where we started to where we finished. And there's our resultant. This would be, in other words, vector A minus vector B, whereas the previous one, the result, was vector A plus vector B. So I wanted to make sure we got that squared away before we move on. Okay. And what I'd like to do next is to use polar coordinates, or the polar form of vectors, and I'll show you how to deal with those using trigonometry. It's called the analytical form, or trigonometry format or method. Okay, so let's say that we have three vectors. Vector A, let's say it's a velocity of 30 meters per second at 30-degree angle, and vector B is, let's say, 50 meters per second or whatever. I'm not even putting units down, at a 270-degree angle, and with reference to positive x-axis. And then vector C is, let's say, 100 meters per second, at, let's say, going at 180 degrees relative to the positive x-axis. So I'll just draw a Cartesian coordinate system here. Here's the positive x-axis, here's the negative x-axis, positive y-axis, negative y-axis, like that. Okay, so we have, if I wanted to just draw those vectors here just for visual, we can see, okay, so 30 at 30 meters per second at 30-degree angle. That's kind of like about 1, 2, 3. I'll make each little segment be worth 10, so 10, 20, 30 for our length at about a 30-degree angle there. Okay, so that's vector A, and then vector B is like 50 at 270, right? Well, 270 relative to this positive x-axis is all the way down here, right? And that would be 50 units, so 10, 20, 30, 40, 50. So I'm not using a ruler or anything, just to get a feeling for it. This would be vector B. And then vector C is 100 going at 180. So that's over to the left there. And that'd be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so there's 100 going that way. Now, let's say we want to find the resultant, but we don't want to use the tail to head method. How do we do it? Well, what we want to do is we want to split each one of those vectors up into horizontal and vertical components. Okay, so let's make a little table here to help us organize our work, and I'll put my x components here and the y components here. And let's do it for vector A first. So this will be vector A, and that's 30 meters per second at 30 degrees. Okay, that's this one here. Well, we can see that if I move that vector A down here, okay, we can see that that vector A can be split up into a horizontal component there. We can call that A sub x, and then a vertical component here. We can call that A sub y. Remember, this is a 30-degree angle. Okay, so let's just use trigonometry now to find what A sub x is. We'll put that in this box here, and then we'll find A sub y, and we'll put it in that box there. Okay, so how do we do that? How do we find A sub x? Okay, well, that's the horizontal component. We know that the hypotenuse of this vector triangle has a magnitude of 30 meters per second or whatever. Okay, so using our ideas of sines and cosine, we see that this is the side adjacent to this angle, so we would use the cosine function. Remember, cosine of, let's say, 30 degrees, in this case, is equal to the adjacent side over the hypotenuse. So that'd be A sub x over 30 meters per second. Okay, so if we want to find A sub x, just use your algebra. Therefore, A sub x is going to be equal to 30 times the cosine of 30 degrees. So we can just put that right here. 30 times the cosine of 30 degrees. And if I just want to calculate that out, I'll find cosine of 30 and then multiply it by 30 meters per second, and we get 25.9. So that's equal to 25.9 for the horizontal component. So this would be 25.9 here. Okay, now let's find the vertical component, A sub y. Okay, remember sine. The sine is equal to the opposite side, which is A sub y, over the hypotenuse, which would be 30 meters per second. So therefore, A sub y is equal to 30 meters per second times sine 30. Sine 30 is a half, so half of 30 is 15. Okay, so this one happens to be a magnitude of 15 right here. Okay, so the magnitude of the x component for vector A is 25.9, and the magnitude of the vertical component of vector A is 15. Now let's move down and address the next vector, vector B, and we'll find the x component, B sub x, and the y component, B sub y. Okay, here we go, same idea. Okay, this time vector B is equal to a length of 50, so we'll make this just using the same approach using this as a model. We'll put 50 in here times the cosine of, let's say, 270 degrees. Okay, so if I type that in, I'll make sure I'm in degree mode. Cosine 270 is 0. How about that? Well, so that means 50 times 0 is 0. Okay, not surprising. There's no width, there's no horizontal component to that totally downward vector there. We didn't have to do any math for that. Okay, how about vertically? Well, it's all vertical, isn't it? So do we need to go and use the sine approach here and do, 50 times the sine of 270? Well, we could. Okay, 270 sine, that's -1 times 50, okay? So that'd be 50 times the sine of 270. That's equal to 50 times a -1. That gives us -50. That's not surprising either. We didn't have to really do any math for that, because we see it's pointing down. That's all negative there, isn't it? Okay, let's look at vector C. Vector C has a magnitude, I'll just put absolute value sign to indicate magnitude, of 100. Okay, so let's find the x component of vector C. Okay, and so we can put 100 times cosine of 180. Okay, and what do we get? Let's put that in. 180 cosine, that's -1. Okay, times 100. So that gives us -100 for the x component of vector C, and then the y component would be C sub y. That would be equal to 100 times the sine of 180. Okay, now sine of this is just all horizontal, so there is no vertical, is there? So the sine of 180 is 0. So this is just equal to 0 here. Now when we want to find we want to add all the x components up, and that'll get us the x component of our resultant, and then add up all the y components, and that will give us the resultant of the y's. Okay, so we go ahead and do that, and I'll just get the handy dandy calculator out, and let's see here, 25.9. Oops, let me try it again. 25.9 plus 0. Okay, minus 100. Okay, I didn't really need a calculator for that, but anyway, -74.1 is the x component of our resultant, and let's do it for the y. We have 15 minus 50 plus 0. Okay, so 15 plus a negative, or minus 50, and that gives us -35. So this is the sum of all your y components. Okay, so that's pretty good. So if we're trying to visualize our sum of the components here, we have our x component that would be -74 long. So let's say it's like this long here, -74.1. That's our x component of the resultant. And then the y component of the result would be like a -35, so that'd still be pointing down. -35 would be r sub y. Okay, the resultant would be from where we started to where we finished. That would be the resultant, and we'd also need to find the angle of that. So how do we do that? Well, we can use the good old Pythagorean theorem. Use the Pythagorean theorem. Okay, so let's do that real quick. Okay, remember the Pythagorean theorem is c squared equals a squared plus b squared, or c equals the square root of a squared plus b squared. In this case, we can find the magnitude r, the vector resultant, is equal to the square root of our x component squared. So that'd be -74.1 squared plus -35 quantity squared. Okay, so if we go ahead and do that, I didn't really need to put the negative signs in there, but I did just so you could see. So 74.1 squared plus 35 squared and then we'll take the square root of that. And I get 81.9 approximately. So 81.9, it might be like meters per second or something of that nature if it's a velocity. Okay, so that's the magnitude of this vector. So this is 81.9 units. But what about the angle theta? Well, what we can do is take advantage of what's known as the inverse tan. Okay, remember tangent is defined in terms of opposite over adjacent. So if we take the opposite side over the adjacent, we can find the angle whose tan would be that. Okay, so the angle is equal to the inverse tan of the opposite, which would be negative 35, over the adjacent, which is equal to negative 74.1. It's supposed to be a 4 there. Let's see what we get for that, and then I'll just hit the inverse tan. Okay, so we'll just go ahead and I'll get my ratio here, 35 divided by 74.1. Okay, that's 0.47, and now I'll get the inverse tan, and basically I see that that's that little blue right there, tan negative 1, so I'll hit the second function to access it, and it comes out to be 25.3 approximately. So the angle is 25.3 degrees. But that's just a reference angle, isn't it? Okay, it's pointing down in this direction, so that would be, you know, greater than 180 if we were using it on a 360 degree reference circle. But it's fine just to put the reference angle in. So our resultant then would be 81.9 units long, and it has a reference angle of 25.3 degrees. So this is how to add vectors using the analytical or trigonometry method. Thanks, guys.